Good morning, champs! Let's learn about differential equations for reaction kinetics. Before I start off with this video, I would really recommend you to watch my previous videos on reaction kinetics. So, having said that, let's start off with this video. So we have a reactor where we have species A, which will react with a rate constant K1 to the species P. Then the species P will react with a rate constant K2 to the species Q. So the task specifies that only species A is available at the beginning of the reaction. Also, we need to assume elementary reactions. So the task specifies that we only have the following information. So we have the concentration of the species A at the time 0, denominated as Ca0, and the rate constant K1 and K2. So in this task, we need to solve the concentration profile of the species A, P, and Q. So let's determine the concentration profile of the species A. In order to do that, we first need to take a closer look into the reaction where A is actually involved. So in this case, A will react with the rate constant K1 to the species P. So, as a quick reminder from our last video, we have said that the reaction rate of a species I is going to be equal to the change of the concentration of the species I with respect to time. And if we know the reaction where the species I is involved, we can say that it's equal to the stoichiometric coefficient of the species I times the rate constant K times the product of the concentration of the reactants, J, elevated to their corresponding reaction order, alpha J. And we have also said that for elementary reaction, we can say that the alpha J is going to be equal to the absolute value of the stoichiometric coefficient of the species J. So again, I really recommend you to watch my previous videos because we have solved numerous exercises using this formula. So the reaction rate for the species A is going to be equal to the change of the concentration of the species A with respect to time, which is going to be equal to the stoichiometric coefficient of the species A, which is -1, times the rate constant K1, times the product of the concentration of our reactants, which is only A in this case, Ca, elevated to its corresponding reaction order, which is 1. So why elevated to 1? Again, alpha A is going to be the absolute value of the stoichiometric coefficient of the species A. So this you can only assume for elementary reactions. Maybe I should write it down. Only for elementary reactions. So alpha A is going to be equal to the absolute value of -1, which is 1. So in the next step, we're going to separate the variables dCA and dt. So to do so, we will just divide with Ca and multiply with dt. So we have dCA on one side and dt on the other side. So on the left side we will have dCA divided Ca equals to negative K1 times dt. So now we can integrate the left side from the concentration of the species A at the time t0, which is Ca0. This is actually given by the task description, to Ca with respect to time. And the right side is going to be integrated from the time t0, which let's say is 0, until t. Just as a quick reminder, the interior from our lower boundary, let's say xl, to an upper boundary xu of dx divided x is going to be equal to the natural logarithm of x with the upper boundary xu and the lower boundary xl, which will result in the natural logarithm of x upper xu minus ln xl, which is the lower boundary. And another reminder for logarithm rule. So if we have, for example, ln xu minus ln xl, this is exactly the same as saying the logarithm, natural logarithm of xu divided xl. So it will apply what we just talked about for the determination of the concentration profile of the species A. We can say that the natural logarithm of Ca with the upper boundary being Ca with respect to time and the lower boundary being Ca0 is going to be equal to minus the rate constant K1 with T with the upper boundary being T and the lower boundary being T0, which is 0. So now we insert the upper and lower boundaries for the integrated part. So the natural logarithm of Ca with respect to time minus the natural logarithm of Ca0 is going to be equal to minus K1 times the upper limit, which is T, minus the lower boundary, which is T0, well, and this is actually 0. So using the logarithm rule we just talked about, we can say that the natural logarithm of CAT divided by CA0 is going to be equal to negative K1 T. And because we want to solve this equation for CAT, we want to get rid of the natural logarithm part. So probably you will know this, but anyways, just as a repetition, I would just say that the exponential elevated natural logarithm of x is going to be equal to x. So we use the exponential. So e elevated ln CAT divided CA0 is going to be equal to e elevated negative K1 times T. So using this rule, we can just say that the left side of our equation is going to be equal to CAT divided CA0 is going to be equal to E elevated minus K1 times T. And for the final step, we multiply our equation with CA0, which will result in CAT being equal to CA0 times E elevated minus K1 times T. So we solved what the task has asked us to do. Nevertheless, I really want to sketch the concentration profile with respect to time. So on the y-axis we have our concentration, on the x-axis we have the time. So at the time 0 we have the concentration Ca0, and the profile will look yeah, something like this.